Thank you. Can you hear me all right? I'm really honored at this invitation. I've actually never physically been at Texas A&M, which has now been corrected. So I'm pleased to be here. I'm going to be talking about linear regression using principal components from general Hilbert space valued covariates. And I want to acknowledge my collaborators, Xin-Yi Li, who has worked as a postdoc with me, is now faculty at Clemson University, Margaret Hoke, who is a PhD student working with me, jointly supervised by Xin-Yi, and then myself. And this is on archive. The paper is currently under review. And I'm going to motivate the question with some imaging data, but also maybe a little more generally. I'll talk a little bit about the overall framework that we'll be looking at. It's a PCA-related framework. Talk about regression theory, some simulations and examples using 2D and 3D imaging experiments, a data analysis, and then a little bit of discussion on some extensions. So I think the motivating example is just that we have a lot of functional data in our life, right? We want to analyze it. Specifically, we'll be looking at some data from Alzheimer's disease brain images. And functional regression is very important. And we might say that why do we need, if it's image data, why don't we just use deep neural nets or something that's known to do really well with images in a lot of general situations? I think that's fine, but sometimes our data sets are not large. Sometimes the specific questions we have, we want to have some interpretability. We may want to construct our models and our methods so we have an interpretation of what's happening. Another thing is that even if we're using generative AI, or let's say a transformer architecture, it turns out that if we use statistical ideas to tailor the architecture, we get humongous gains in performance. This has been recently demonstrating for using time series theory, applying it to transformer and getting results that perform much better than any of the alternative standards in the AI community. And so in general, I feel that this approach is still very important, even if we want to eventually use AI for these questions. So Alzheimer's disease, a leading cause of dementia, affects memory, language, and behavior. Imaging matters because a lot of the structural changes in the disease can be observed in humans, and sometimes we get warning from the images of more than a decade before the onset. And so here's an example of different images of one particular slice, two-dimensional slice from PET MRI images. There is some differences. They're somewhat subtle, but you do see some different areas that are darkening, some different sizes. We now know that there's a huge amount of information there, but it really helps us when we're able to hone in an interpretable way on those features of the images that are relevant. So the statistical challenge is how do we combine image data, for example, with other tabular type data such as genetics and clinical risk factors to jointly be able to understand what's going on with this disease, among other reasons for this, which hopefully will become apparent as we proceed. So the risk factors for Alzheimer's disease are a lot. We have age and gender, education, intellectual activities, marriage, family history, the genetics, and many, many other things. And this can be related to mild cognitive impairment, and it can be related to how severely and how soon this moves into full-blown Alzheimer's disease. So this is one of many components that are needed for understanding this, the images. So brain images are naturally modeled as random elements of an abstract Hilbert space, but existing methodology falls short. And this is where there's a lot of really good methods, but I'm going to try to articulate a little bit clearly. So one of the challenges is that this is multidimensional data, more than two. One-dimensional functional methods are not going to work. There exist two-dimensional methods. I'm just trying to emphasize that. Irregular geometries, tensor product approaches impose an artificial grid structure, at least currently, but there's some nice features about the tensor-based approach also that can be utilized. This is very high dimensional. We can have a single image can be 500,000 voxels of information in 3D. And so naive analysis is not very feasible. One could probably just throw an AI model at it and see what happens. People do that. If it may or may not work, but that seems to be a relatively uninformed approach. It seems natural that many of these can have an inner product structure and that can kind of guide in the thinking of models. And with that, Hilbert spaces become very natural. And separable Hilbert spaces are a very rich example. Separable is an assumption that we'll use, but it's extremely general. It just means there's a random variable that there exists a separable set where that feature exists. It doesn't have to be, it can be embedded in higher dimensions. And this turns out to show up a lot. For example, if one looks at weak limits of even extremely complex high dimensional Donsker processes, let's say Donsker classes, those can be immensely high dimensional. Most weak convergence theory applies to separable limits. So at least we think of certain features of reality are at some level modelable as separable. You can also break separability, but I'm not going to go into that right now. But these are fairly reasonable assumptions in a lot of settings. So the model, one model we could look at is a very simple linear model where we have an intercept term, some tabular data x of some dimension d, and we have a Hilbert's valued space, a covariate random variable, and we have an unknown inner product gamma, and then some residual error. For now, we're going to just use scalar outcomes. Our goals are an interpretable finite approximation of the gamma prime z portion here via PCA use, principal component analysis of z in the Hilbert space. And we're also going to work towards root n consistent asymptotic normal expansion of all the parameters, including the functional parameters that are in gamma. Because as we see later, but gamma needs to be in the same space as z, right, for this inner product to work. So at a very high level, what's been done before? I'm not going to summarize the many decades of beautiful work in this area entirely, but I'm going to talk about the stuff that's most relative to where our point of departure is. So there has been some wonderful work on PCA theory, going back to Koczyński and Luisi, looking at effective rank, spectral projections. One of the key gaps, it's not clear how to incorporate into the regression pipeline. And the covariance kernel is assumed known. So these are often assumed to be a reproducing kernel Hilbert space, and so lots of great things can be done there. That's actually a special case of a separable space, just as I mentioned there. So, but you have to know that kernel in advance. Sometimes that's reasonable. With time series data, you can often use, for many situations, you can often use Fourier type bases that work very well. But in higher dimensions, that's tricky. The good work by Yuan and Tsai using reproducible kernel Hilbert, and Shi et al. And Li et al., where they were able to obtain optimal minimax rates for functional regression. Now, these are not root n consistent, but they're clearly the minimax rate. But you don't get joint Gaussian limits for eigenpairs or valid regression inference in the root n setting. So we want to try to do all of those things. We want to not have to specify the kernel, and not even have to, well, and be as general as separable. We want to look at joint Gaussian limits for the eigenpairs that we figure satisfy our level of accuracy we want to look at, and root n inference for regression, with abstract Hilbert space-valued covariates. So 3 contributions of this work are first, a way of looking at PCA for Hilbert space. We don't require kernel specification. It's purely data-driven. We do have a data-driven projection diagnostic to evaluate whether our projection that we're using is good. Consistent component selection, meaning based on principle, controlling the variance of how much of the variance of Z we explain. Our later work, we're able to do more specifically on controlling the variance of Y. That's a harder problem. I'm not going to discuss that today. We only require separability plus 4th moment of the norm of, this is the norm that's in the embedded space, the Hilbert space. We develop inferential theory. We have an extremely general Donsker theorem, which is surprisingly general. And it requires 4th moment if you're looking only at one covariate, but if you have many and interaction terms, it turns out that you just need certain moments to exist. It's a little bit more of them when you have interactions. We don't require Gaussianity. There's no rank constraints per se. And we, as far as we know, this is the first complete principal component theory of its type for this general setting. We also can readily incorporate Euclidean parameters into this work. Turns out that one just has a tensor product space that includes both of these things, and everything can be embedded in a larger Hilbert space. Yeah, question? It's fully observed. We like pixel-based data. Yeah. As near as possible. We'll talk about that in a little more detail in just a moment. But that's a very good question because they could do this several ways, right? Usually fully observed is not feasible for most instrumentation, but you could do pixel-based and then ignore the pixel structure or not have be able to not be intimidated by the fact that the pixels are high dimensions. The pixels could be a starting point, right? That they live in a huge Hilbert space, right? Or there's another alternative. We'll use a particular type of triangulation approach. And that does raise one of the questions is we do need, for this work to work, we need preliminary, some sort of working bases. They don't have to be orthogonal, they don't have to be complete, and they can definitely be overspecified. And we'll talk about that. But we'll come to this a little bit more, but make sure I answer your question. If I don't, call me out. But we can obtain bootstrap confidence intervals for all the parameters as well. So first, adaptive subspace PCA. I'll talk about that. So the nice thing about the separability assumption is that you get to use the Cahoon-Loewe expansion. And it has this form here. This is well-known property, general property. We're going to assume that C is separable and also that the second norm is bounded. I know later I'll need higher bounds on the norm, but this is all we need for this step. And if you have this, you can represent it in this nice way where you have an infinite series that starts from the largest eigenvalues and goes down. They have to be, they're positive. And we assume that the sum of the lambda j's is finite. Sorry, that's a consequence of the assumptions. You'll automatically get the sum of the lambda j's are finite. You get the eigenvalue, you get the expansion up there. You also get that the eigenfunctions form an orthonormal basis of a subspace, very well-defined subspace H0 of H. It's a separable subspace. And the scores are uncorrelated. They have variance 1 and their mean 0. However, they could be dependent because we're not assuming Gaussianity. And they could have, if you look at interactions among higher order terms, they may not go to 0 as you would have. Okay, but all of the thing about this though is the mean and the eigenvalues and the eigenfunctions are unknown, right? So our goal is to rectify that. So the theorem is basically, this is a well-known result. The only, we added another corollary to this later on where this automatically means that if you look at the inner product of Z and the unit ball in this in the embedded Hilbert space, that entire functional set is Donsker, which is somewhat surprising. Although the existence of that central limit theorem has been known, the generality is a little bit surprising. Okay, three-stage estimation procedure. You need some sort of basis to work with. And so in this case, what we do, we'll find later, is we use a particular type of spline that can fit on a triangulation where all the edges touch and they're smooth. So that type of spline is very easy to work with. You can extract it from the pixels. You can do it in other ways. You can get them. And we don't need that to be full rank or in any sense. And what we show is, what we do require though, is that if we look at the projection on the centered Z of this, that the difference between that projection and the original thing goes to zero. The expectation of that squared is little o n to the minus one. That sounds like a very strong assumption, and it is. Fortunately, we can actually test that assumption. But really, you're talking about making sure you have a rich enough set. The nice thing about this type of triangulation we'll talk about is that you do have, now you have a smooth surface, even if you started off with the pixels. And it's good for a lot of other things as well. But this doesn't have to be the only. You could use the straight up pixels. That's technically a Hilbert space too. You could use that and embed it in that as well, the raw pixels, but we don't do that. It doesn't seem to work quite as well as what we choose here. And we'll develop a diagnostic, which is an estimate of delta n, and we'll show that we can evaluate whether we have enough bases. Because there are some things you can compute. Somebody mentioned, I have to be able to compute the norm, okay, of this, the data, the raw data. And so second step is we build an empirical covariance matrix Mn hat, and we can fairly straightforward. This is not hard to do. This is just a matrix. We can do Gram-Schmidt normalization of that matrix. We get, if it's rank L, we just focus on the non-zero eigenvalues. And then we get our functional terms by just taking the linear combinations in the next slide 3 here of the original bases. And so now these bases are new. They're just computed fairly straightforwardly by this process of you do the inner product matrix first, and then you do the eigenvalue decomposition of that, take the non-zero ones. Eigenfunctions, you can take those eigenfunctions, and they're the weightings for your original bases. And this gives you new bases that are orthonormal. And so that's our starting place. They aren't necessarily the Cahunin-Loew expansion, but they're at least orthonormal in terms of their inner products. Yeah.
Eigenvalue can just come to the finite sum and then expansion.
Well, so these are estimates, right? We know the underlying true ones. We believe if the norm is there, that has to be the case, right? If it's separable plus second norm, you have to have this expansion exists, right? And so we don't know what it is. And so these are estimates. We're trying to estimate it, right? So this is a starting place. I haven't yet taken these and created the orthonormal ones, but these are nice because they have some properties where their inner products are zero with each other, right? Their norm is 1. And so this is going to be easier. This is a first stage. This is going to be easier set to work with. Does that answer your question? Maybe see if what I say helps. But this is just simply computing from the working bases and with the existing data that we have. Okay, so going back a little bit more on the triangulation, triangulations there are algorithms for doing this, and they're a very nice thing to do, and they can adapt to a variety of things. Now you have to have some sort of registration where these images are comparable. That alone can be somewhat challenging. Modern equipment makes that fairly easy though. And so the initial spline bases we use are, we use the simplex that comes from these little triangles, right? And you can create these splines that are potentially linear dependent, but you get a lot of independence because each triangle has its own set of splines, even though it's constrained to be smooth to its neighbors. And that gives us our initial basis. And why do we do this sort of triangulation? It allows us to handle fairly irregular domains. Approximation theory guarantees assumption A2, which going back here, which is what A2, that this will allow us to be able to establish that this is at least reasonable, even though we can also test it, but we believe that this will let us establish that and give us that. It works in 2D and 3D without a lot of modification. And in fact, there are other extensions of this. If you have time series of brain images, the tensor product of these bases can work as well. And it appears to be superior to tensor product kernels for neuroimaging. So the theoretical basis comes from some papers by Lian Wang and Li et al. Okay, so before I get too far along, so I still haven't discussed how to estimate from this yet, how to estimate these bases. But you start with these bases from these triangulations, which is computable, and then you do this you have an inner product matrix where you take all the inner products of these guys, not with data, just by themselves, because they all have inner products, right? You form the inner product matrix, which is high dimensional. With that, and each of the rows and columns correspond with a particular functional component, right? The spline, right? And so then you do eigenvalue decomposition, take your non-zero eigenvalues, and now your eigenvectors become the linear combinations that go with this z, and you have your lambda as well, although we're not necessarily using the lambdas yet. The other thing you have to do is there's another step I left out where I take the generalized inverse of lambda to the 1/2 power, and I use that to normalize these. Okay, so I've normalized and orthogonalized them. Still a question back there?
When we clarify, pre-processing of them, just get the standard frame.
Yes, using existing software for that. So it's not the raw data. Yeah.
Large enough of the order of log of something like that, your assumption should be satisfied.
Yeah, because we only require, it's basically slightly faster than square root of n of the norm, right? Because I took the square of the norm. Yeah. These are a huge number of bases, and every triangulation in that little region, you have a lot of independence from others. So it's sort of like an informed type of pixelation almost, where there's lots of continuity that you're utilizing. That makes sense? N can be gigantic, just can't be infinite, of course. That's be computationally workable. Yeah, but it turns out that then once you do this, the number of, when you're finally done with this process, the number you have is not always as big as the sample size even, depending on what you've done. But you want to, so I'll come to here. I'll come to the way to evaluate this, the simple data-based approach to check to see if your spines are working. So here's the Donsker theorem that is actually the engine that kind of runs a lot of the results here. So Z1 and Z to ZK be random elements in the separable Hilbert space. They don't, each of them, they don't have to be the same Hilbert space. And assume that the products of and these are mean zero. These have to be mean zero. In this stage, we'll allow for general mean in just a moment here, but take the squared norms, the product, and have that be finite. In the case of just looking at z, this is where you get, when you do a covariance, you need the product of z squared, so that gives you the 4th power. But then you have that this entire array, the products of all these inner products between the entire unit balls for each of their Hilbert spaces is a Donsker class, which is somewhat a surprising result. It only requires finite second moments, well, 4th moments technically, but the products of second moments. We're not assuming Gaussianity, we're not assuming any sub-Gaussian tails, and no rank constraints per se at all. And this guarantees that our empirical covariance operator will behave as a tight Gaussian perturbation of V0. That's really where we get to do a lot of this. And this drives a lot of downstream analyses. Okay, before the main estimate results, we need one identifiability condition on the eigenvalue structure of V0. This is not strictly necessary for everything. It just makes everything easier. That's a spectral gap assumption where the eigenvalues that you're going to be interested in focusing on, they need to be ordered. And it turns out that's not easy, but it's not super hard to generalize this. It's just complicated beyond the scope of this particular presentation. So the leading M eigenvalues of V0, we'll find out how to decide M in just a minute, but that's what we'll need. We only have to have well, the gap is not, without a gap, we have trouble with the eigenspace and formulating what a projection looks like in higher dimensions than 1. You can do it, but it just requires a little more math than we have time to discuss here. So imaging covariance operators tend to, from our observation, have well-separated eigenvalues in practice. If ties occur, the eigenspace projector is still consistently estimated. Only individual eigenfunctions require A3. So we can still get the eigenvalues themselves. So this gap will be part of the variance for the limiting value of the functions. That's where that gap comes. At least because we're doing it for just one-dimensional. Anyway, yeah, so that's, okay. So under these constraints, we get uniform consistency. With the fourth moment added, we get asymptotic normality for all of these up to the M of the joint asymptotic normality of the eigenvalues and the eigenfunctions. I'm not giving you the full linear operator here, but it turns out that what the curly, the fancy little letters in there, those are linear functionals that are, I have them specifically in the paper, you can see them. They're just lengthy to describe. But this is this gives you, when you have, this is basically stronger than just asymptotic normality, right? This gives us, this is asymptotically, these are additive estimators, right? And so this means that with that, I automatically get asymptotic normality of functionals of these as well that are smooth. And so this gives me a lot more, and I can add it to something else. If I have two things where I've separately done this, that means jointly you have asymptotic normality too. So this asymptotic linearity really, really helps the influence function. Okay, so here's a projection accuracy in my clock. Oh, there's the clock. Okay, projection assumption. What we do is we estimate delta hat by taking the sum of the squares of the differences between zi and their means, and then just empirically, and then the mn hat matrix we had before, we subtract the trace of that. And that is exactly a consistent estimator of this. In fact, it's consistent at enough higher order that we can construct a test statistic, Tn hat equals the square root of n delta n hat divided by something s hat, which is a way of estimating the covariance of this. And we get almost asymptotically precise limiting distribution, but not quite. What we get is that if I pick a critical value, say z, if Tn hat is greater than z1 minus alpha, I would need to increase my richness. If it's not, I'm okay. And we're looking at this local alternatives here. We can get this boundary that we can get a consistent test, but we can't get to the point where we have the limiting distribution so I can actually give you precise power. But this does mean that for any actual, if there is an error, if I have enough data, I can find it, all right, of this order. Okay, so our population targets, we had to do principal component estimation. We want to get up to 1 minus tau of the total variance of z explained. We then take our estimated eigenvalue. We take 1 minus tau times this Pn hat I mentioned of the covariance variance. And when Mn hat, just the smallest m that's bigger than this, we have to assume that's how far we have to go. And if our underlying function has a gap, spectral gap to that degree, we will be consistent in finding it by this. It's basically like using a scree plot. Okay, so I'm going to have to move a little bit here. The oracle regressor is where we know the principal components, and we have a feasible regressor. Our idea now is to use the principal components to control the variance and then use those in our regression model. A question you might ask is, say, but does that guarantee variance control in Y? The answer is that's a much harder problem, but this is a start. At least you're capturing the structure of Z, the majority of the structure in Z. We actually have a solution to that other question, but we're not ready to present it yet. But in any case, at this stage, we can do this regression now. We can estimate the principal components, and we can prove that it's consistent. I'm going to kind of move a little faster. We now have that the principal components here, going before, here is where we actually have asymptotic normality of the principal components themselves, the vectors. So it's a little surprising. Those working with semiparametric know that normally with semiparametric models, we can't get faster than root in. So what is going on here? Well, there are several situations where you get approximate regularity. This happens, for example, with the cumulative distribution function, the cumulative hazard function, survival function, where you have that the entire function is asymptotically Gaussian, right? And you have regularity, enough regularity, you can do weak limits, weak convergence of the whole thing. Well, we get enough structure here. It really stems back to the covariance. The covariance being Donsker really gives us this ability to do this. And so it's kind of an interesting thing, a little bit surprising to us, but it's not necessarily impossibly unexpected, meaning it doesn't contradict anything we know. Okay, so here is what we can now use these results before to give us a full expansion of square root of n of theta n hat based on our using estimated eigenvalues minus the true theta naught if we had the oracle eigenfunctions and we were fitting the same model. And it has a linear operator structure here. There are two pieces, and this is just not time to give you the whole details here, but the first term is the least squares component itself. The second term is from the principal component estimate, that really were driven by the covariance estimator, the consistency of the Donsker properties of the covariance operator as an operator. Okay, so the difficulty of this is there's not a nice closed form. The form of that linear functional, that you cannot estimate the parts because it requires knowing all the eigenvalues to infinity to estimate the linear operator. The existence of the linear operator, though, means that we can do bootstrap. So the linear operator itself is not estimable directly. That's usually what's done when one wants to get asymptotic normality covariance estimate, is you have an operator you can estimate. We can't because we don't know all the eigenvalue up to infinity. And so, but we can do this thing, which we can do a non-parametric bootstrap of different types. We can use a wild, which is basically a Bayesian bootstrap, and other types of bootstraps. And that is still working and will give us the results. That means we have to bootstrap the whole thing. We've bootstrapped fitting the principal components, selecting them, and then going. Actually, the selection we can stay fixed because that's consistent. That's an L0 convergence issue. So you just need to refit the eigenfunctions and the regression with each bootstrap. And it works. So I think I'm okay. I kind of went that a little faster than necessary because I have 10 more minutes. I want to cover things, but I can slow down if there's any questions about the theory. It's a little bit at a high level, I realize. Okay, with simulation studies, the long and short of it is that we simulate a bunch of these higher dimensional quantities using our own bases that were created for this. So the procedure doesn't know these bases, but we can generate them to see if we recapture them. So we're going to evaluate in simulations eigenvalue accuracy, eigenfunction recovery, component selection, does it consistent selecting the components, and then regression accuracy, and then bootstrap, validity of bootstrap coverage. This does assume that the linear model that we had initially is true. we're working on what to do under misspecification, but we do require there to be a linear model. Okay, so here are on the left four are our, this is a representation of the four bases that we have in the simulation process. Sorry, I'm wrong. 6, we have 6 across the top. Those are our 6 bases in the simulation. And in the recovery is our estimates down below. You can see visually the key structures are pretty clearly captured by this approach. It is able to successfully estimate them without knowing them in advance. And they're kind of interesting principal components. And then what we also do are the eigenvalue consistency, and here's the mean squared error. It starts off pretty big with a sample size of 100, but it gets down to reasonable fairly quickly. Bootstrap confidence coverage is pretty good. It's a little bit conservative for 100, and sometimes up to even 500 it can be anti-conservative, but it's generally at least conservative by the time you get to 1,000, a couple thousand. And this is just different parameters are converging at different rates. Convergence is slower when the spectral gap is smaller, for example. But it does pretty well, it seems. And so we also did this for 3-dimensional volume. Here it's a little bit harder to visualize these without having something I can rotate around. But we have our estimates look pretty close if you just compare. You can see this is a relatively simple spherical, sort of approximately spherical thing, but at least it shows that we can capture something. They have to come up with better ways to visualize 3-dimensional images. What a physician will do is rotate it so they can see different aspects. And so these are rotatable. I just don't have time to prepare that image for you all, but it seems to recover pretty well. For the application, we have a data set that has images. And the MMSE is mini mental severity score. So this is from 15 to 30. I believe that the higher the score, the better the person's brain. So you don't want low scores here. But this is a score that's fairly easy to administer and pretty reliable. So lower is more severe, as I said. And it's integer valued. Y, so Y is fairly simple. Clearly it has bounded second, fourth moments. Functional coverate is a brain image. And we're using 2-dimensional for this demonstration. We can also do 3 though, as I mentioned. And so there's, they're gonna have, each pixel we have a continuous value. Okay, so that's what, in this case, it's more glucose activity, which indicates more activity generally, because that's a precursor to activity, right? We have age, education, sex, race, ethnicity, marital status, and a genetic predictor, APOE, which we also have, and it'll just be from 0, 1 to 2. Okay, so here's our regression estimates, and from our principal component as well that we have. And what we've done here with the principal component is we've taken all of our components and put it into one gamma, so you can see all of them together. Because remember, it's an interproduct between gamma and z. This is the gamma hat down below. And what we see are what we might expect in the direction. Better education leads to better scores. As this is unfortunately an aging phenomenon, so aging risks go up, and there's a few other things there, and there's some clear evidence, especially stronger with 2 copies of the gene. And this, one thing that's interesting a little bit to me about this image is it's not symmetric. It seems to be highlighting stuff on the right side of the brain, both in the frontal and in the back, frontal and whatever the other one is, the back one is, right-hand sides, the lobes. And so that's interesting. And this, so our collaborators find this interesting. So briefly, I'll just mention that we are extending this to precision medicine, where we're trying to use this to identify the ability to use the images to help guide treatment selection. So in this case, we have a simple binary treatment. We simply do a different regression model for treatment 0 versus treatment 1. Question is, when is it advantageous to start this treatment? And the treatment main effect is pretty large. It's almost 10 MMSE points, which is clinically highly significant. The other parameters make sense. Gamma hat reveals brain image where PET metabolic patterns predict differential treatment response. I'm not presenting that here. But this is our original motivation, actually. So future work includes doing this when we don't know that the model is correct. What can we get out of it? What works? It turns out that we can still do much of the same theory. There's just some interesting things that happen. And we're also generalizing it for other things like generalized linear models, eventually for working towards random forests that incorporate these, as well as generative AI that incorporates these as well. Those are not yet very far along. Okay, so do I have time to summarize briefly? Yes, good. In summary, we have developed a kernel-free data adapted PCA framework for random elements in any separable Hilbert space with bounded norm moments, with projection accuracy and consistent component selection. We have a Donsker theorem, which is really the engine. And this, I just want a little bit about the proof. This does not arise from VC type class arguments or other ones where we have various tools for building it. We have to go more towards a foundation. The kind of the thing that really works here is the fact that when we have a finite number of Hilbert spaces, the tail bound of that infinite sum, we can clip these things at a certain n successfully and get an error bound, a bound that works in root n level. And then we have finite dimensional bounded space afterwards, which is much easier to work with. The trick is that last step. I made it sound simple, but that was where a lot of work was involved to get that to happen. But that's the basic idea. Root inconsistent regression is another contribution. The Donsker theorem, the second moment is needed for the inner product of Z and gamma to be, or gamma is a unit ball to be Donsker. You need the second moment if you want the covariance operator to be Donsker too. We got root inconsistency for the functional components as well as for the other components. And it appears to work well when we analyze data. And our data sets are much smaller than our simulations. So there's, again, some things require bigger sample size for everything to work out, but it seems to be performing well at modest sample size. So other things we're interested in are incomplete noisy observations of these, sparse functional data settings of certain types. And I think we want to work a little bit more on the tensor product and look at some of these much higher dimensional Hilbert spaces I mentioned are theoretically possible. So here's some references, and that's it. Okay.
Them together in the same model. We made them because those parameters are low dimensional, but temperature powerfully predict the outcome. My second question is, can the method be applied, for example, structural MRI data during PET?
Answer is yes, so both of those things. I believe, yeah, in our example here, we have tabular data with image data. But remember, the method is agnostic to the actual Hilbert space. And so, I mean, it does need to be separable. And I could talk a little bit more about what that means, but it tends to be that most images behave separably. I mean, for example, if the different things, it's a chaotic behavior that you would have trouble with. You have highly chaotic behavior on the edges of something. If you can, shave that off, you'll ensure. So this can not necessarily handle everything, but the images you described, even if they're higher dimensions, like for example, video data could be something that could use this, and multivariable versions of this. Let's say you have two imaging modalities, You might do the principal component thing, control the variance for them separately. Then you can bring them all into the regression equation. In addition, you can have higher order interactions between those and the tabular data. Any model you want. The challenge is those all require higher moments, right? And if that seems reasonable, then you can proceed ahead with richer model. Of course, the usual concerns with having, what's interesting about this brings these high infinite dimensional things down to a modestly number of finite dimensions. But if you do that a lot of times with a lot of dimensions, you're going to have similar issues, right? And so there it might be good to look at even principal components to reduce further the dimension. Great question. Yeah.
Started with blind PCs and they are not orthonormal, so we do a PCA. So why don't instead of blind basis, we start with some orthonormal basis so we can skip the PCA step because you already have.
So good question. If you have orthonormal bases, that just means your inner products are orthonormal. It doesn't mean their Cohen and Loeb expansion works. So you won't necessarily know how much variance you're controlling, right? You won't have a systematic way of controlling variance. But maybe you could do principal components on the projections. Is that what you're talking about? I don't fully understand your question. Yeah, because there might be, the advantage of this is that you now have principal components which could be interpretable in their own right. So this can lead to interpretable models potentially. And also you have the guarantee that they explain a certain amount of variance and they're stochastically uncorrelated with each other, right? And so that gives you a lot of power when you do your regression models, right? The diagonal covariance matrix it's just diagonal. And so there are a lot of post-analyses that are much improved as a result of this, among other things. But that's a great question. Yeah.
Believe that people like to practice or some restriction on ability of eigenvector. You were using Dunstan type process. Are the two related or Dunstan?
Yeah, they are related. And so what happens, let's just go back to the first assumption, separability, and then I have second moment of the norm. We're just ignoring, assuming mean zero for now. The mean everything works with the mean, it just adds another layer of complication. The Ornstein-Uhlenbeck falls from that, and the summability of the eigenvalues falls from that automatically. So you have that, and then you can use that in various ways. I don't know if I'm making sense. You can use the summability of the eigenvalues in different steps. So actually for the, what happens when you have a tensor product, the new space also has summability of the eigenvalues, right? And if you have additional norms, you can control the tail of those sums, right? And so that's really the kind of thing that we're doing. Because historically, people looked at more structural assumptions, very specific behavior of the eigenvalues. Now, I will say that our test, we do have to have some slightly stronger assumptions on the tail behavior of the random elements, right? There, we need to have that for each, the UIs, we have to have that the fourth moment of the UI divided by the square of the second moment is bounded. It doesn't go to infinity because that that's only for the test thing. We don't have that problem with wild behavior. Turns out things are very well behaved for all the other things we're trying to do. But for that test, we actually need a stronger assumption on the tail. So we're trying to minimize those extra structural assumptions as much as possible, but sometimes we need parts of them for when we go down for the test. For the regression, we don't. Just for that test that you have enough, your basis is strong enough. Does that make sense?